All right, today we're jumping right back to the absolute basics, the physics that makes everything we do in wireless possible, the electromagnetic wave.
So this is part 2 of our big deep dive into RF propagation. It's all designed for you, the techs and engineers out in the field. We're basing this whole series on a really detailed report from RFI detectives, and today we are laying the foundation that absolutely everything else is going to be built on.
Okay, here's the plan. We'll start with what a radio wave actually is, then we'll get into the single most important equation in all of RF. After that, we'll break down a wave's key specs, see how it actually talks to our hardware, and then wrap it all up by connecting it back to our day-to-day work.
First up, let's get a really clear picture of what a radio wave is, because you can't really master something until you understand its fundamental nature and what makes it so unique. Here's the most important thing to get straight. A radio wave is not like sound. It doesn't need air or water or anything to travel through. It's pure energy, a disturbance that travels all by itself. You've got these electric and magnetic fields dancing at right angles to each other, zipping along at the speed of light. And that distinction right there is everything. Okay, now let's get to what is, without a doubt, the single most important relationship in our entire field. If you only remember one thing from this whole explainer, make it this. And there it is. Wavelengths equals the speed of light divided by frequency. It looks so simple, right? But this is basically the Rosetta Stone of RF. It creates this perfect inverse relationship. As frequency goes up, wavelength gets shorter. This little formula is what connects the invisible idea of frequency to the very real physical dimension of wavelength. And that connection, well, it dictates pretty much everything else. And this is where it gets really practical. I mean, just look at the difference here. At 500 kilohertz, that wave is 600 meters long. It literally sees things like hills and valleys. But then you jump way up to 5 gigahertz, and the wavelength is just 6 centimeters. Now it's interacting with things like raindrops and window panes. It's the same kind of energy, but a simple change in frequency completely alters how that wave experiences the world. So, with that key relationship in mind, we can now break down any wave into 5 essential parameters. You can think of these as the basic specs that tell you exactly how a wave is going to behave out in the wild. Think of this as the technical data sheet for any radio wave you're going to deal with. You've got amplitude, frequency, wavelength, phase, and polarization. So let's just do a quick lightning round on each one. Amplitude is just the raw power of your signal. It's strength. And as we all know, that strength naturally drops off as it spreads out over distance. We call that free space path loss. This is the #1 variable in every single link budget you will ever calculate. Frequency, well, that's the driver. It really defines the wave's whole personality. Is it going to be a ground wave and hug the Earth? A sky wave that can bounce off the ionosphere? Or is it a microwave signal that needs a perfect, clear line of sight? Frequency determines that. And wavelength, of course, is the direct physical result of frequency. It's the literal size of the wave in space, and it's what tells you whether a building is going to be an obstacle, a reflector, or completely invisible to your signal. Now, phase might seem a little abstract, but believe me, it becomes incredibly important in the real world. Why? Because you almost never get just one clean signal. You get reflections bouncing off of everything, and the phase relationship between all those signals is what determines if they add up and make your signal stronger, or cancel each other out and kill it. And finally, we have polarization. This is just the orientation of the electric field. Is it wiggling up and down, side to side, or spinning? Whatever it is, if you want to get the best possible signal, your receiving antenna has to be polarized to match it. It's as simple as that. Okay, so let's see how this all connects. How do we actually grab one of these invisible waves and convert it into a useful electrical signal? This is really where the theory meets the hardware. I mean, that's the whole magic trick of what we do, isn't it? We're bridging the gap between this field propagating through empty space and an actual current flowing down a wire. And the answer, of course, is the antenna. The antenna is our translator. It's a resonant device, which is a fancy way of saying its physical size is custom built to be super efficient at one particular wavelength. It's perfectly tuned to either launch a wave out into the world or to grab its energy with as little loss as possible. And this slide right here really closes the loop. Remember that fundamental equation we looked at? Well, here it is, but made of steel and wire. A half-wave dipole antenna for a 7 megahertz signal is a whopping 21 meters long. But for a 5.8 gigahertz Wi-Fi signal, that same type of antenna is just over 2.5 centimeters. Wavelength directly becomes hardware. So why did we just spend all this time going over these core ideas? Because these aren't just details for a textbook. They are the absolute foundation for every single practical decision that we make in the field.
Mastering these 5 things isn't just an academic exercise, it's an operational necessity. When you're troubleshooting a bad link, you're really just troubleshooting one of these 5 things. When you're designing a new system, you're building it based on these 5 parameters. This is the language of RF.
So, okay, we've got the fundamental building blocks down. But how do these simple variables cause such dramatically different behaviors? How can one signal bend with the curve of the Earth while another gets stopped dead by a few trees? Well, that's the big question, and that's exactly what we're going to dive into next time.